Alright, so today we're going to be talking about properties of minerals or characteristics that each mineral has that help us identify it in the field. Even though there are thousands of minerals that have been named, last lesson we learned that there's 3,800 of them at least. There's only about 90% of them that we'll encounter in the field on a daily basis. So using these properties or characteristics, we're going to be able to identify about 90% of those things. Minerals, as we learned last time, are based on their chemical composition, which is expressed by their physical properties. So those elements and how they combine on the periodic table to form minerals is going to be expressed in the things that we're talking about today. Some of those things include color, crystal form, hardness, density, luster, and cleavage. A lot of those words are on our vocab. This right here, our objectives. We will utilize the 6 physical properties of a mineral to identify them. Here's a picture from Mars. This is on Mars. Geologists have recently discovered geothite and hematite exist in an abundance on Mars. We have hematite here on Earth. If you look back or remember from our last lesson in those mineral groups, we have this rusty red color, which leads us to believe that this is an oxide, which in fact hematite is. So on Mars we have these little pebble things, which they call berries. And when they tested them in the laboratory, they found out that these berries were made out of Fe, which is iron, and oxygen, O3, meaning that there is rust on Mars, which leads scientists to believe that there was once water. So these properties of minerals that we're seeing expressed through their atomic structure apply not only to Earth, but to our space explorations as well. The most common minerals in Earth's crust can often be identified in the field using basic physical properties such as color, shape, and hardness. The context of a mineral is important as well, or where it's found, what types of things are around it. Some minerals can form under the same conditions, so you're likely to find them in the same rock, while others are very different conditions and will never occur in the same rock. To put that into context of what we have in Colorado, a lot of what you get up near Pikes Peak is made of Pikes Peak granite. Pikes Peak granite formed from magma cooling very slowly underneath the ground. So as you're up in Pikes Peak, if you find a mineral, it's unlikely that it's going to be something that formed from like obsidian, from magma cooling really fast, or something that's forming from a hydrothermal solution if there's no hydrothermal solutions around. This silicon, oxygen, aluminum, iron, calcium, potassium, magnesium, and sodium are the most common elements that we find on Earth's crust. They call them the Big 8, and they make up all of these minerals that we're seeing down here below. If you remember from our last video lecture, in our groups, our silicates are the most common. So of these minerals down here, most of them are going to be silicates. Our quartz, our muscovite, our biotite, our olivine, feldspar, hematite. Oh, no, hematite is a oxide, sorry. So all of those are going to be silicates, and then the rest of them will fall into another group. Color is going to be our first property of our mineral. Although it's the most obvious, it is the least diagnostic or worst one to use. There's a couple reasons why color is so bad. If we take a look at this chart of a bunch of different known minerals, we could count at least probably 10 ones that have the color green, 10 to 15 that are a silver color. So the color isn't going to work out very well for giving us a definite answer because so many things are the same color. In the same regard as that, one mineral can take on many different colors. Quartz, for example, can be that clear white iridescent color, or it could be pink, or it could be black. This is because impurities go into the crystal while it's forming, so as our atoms are self-arranging and making that structure, an impurity like magnesium or iron or something can get in there with the silicon and oxygen of quartz, and it will taint it a different color. Another part of the reason that the color of minerals is not uniquely diagnostic is that there's several components of crystal compositions and structure that produce color. So the presence of some elements such as iron always results in a colored mineral, but iron can have a wide variety of colors, especially if it's being oxidized. So as our iron rusts, it can be on a shade from a smoky gray to a green to a red. Some minerals have color-producing elements in their crystal structure, such as olivine, which is that green one that we were looking at last video, and some of them incorporate impurities like quartz, which we already talked about. This variability makes it difficult to solely use color as the only indicator for a mineral. However, color can help us a little bit. In this picture, we have hornblende biotite and muscovite mica. If we were hiking around and we found a dark colored rock, we would identify it probably either as hornblende or biotite. However, biotite is very flaky. It forms in sheets, whereas hornblende is a heavier, denser, more solid rock. So depending on color plus other things, color definitely helps us out figuring out whatever our mineral is. The next thing we're going to talk about is crystal form. Crystal form is the external shape of the mineral crystal. We talked a lot about this on last Friday when we did our self-arrangement. Mineral crystals line up and they're going to give us a specific shape. So in this one we have a cubic crystal form, a prismatic crystal form, and an amorphous crystal form. Certain minerals like salt or halite have cubic form. They're always going to look like these cubic shaped squares. Other ones don't form regular shaped crystals, so they're called amorphous. We'll look more at different crystal shapes later. The next thing we're going to talk about is hardness. Right here you'll see Mohs hardness scale. Hardness of a material can be tested in several ways. Most commonly, minerals are compared to an object of known hardness using what we call a scratch test. The scratch test you need to become extra familiar with. We're going to be working with it in class next time. When you start the scratch test, you always want to start down here at the bottom with the fingernail. So we know that a fingernail has a known hardness of 2.5. As we scratch an object with our fingernail, if the object flakes off, then the mineral is going to be less than 2.5. After that, we have a penny, which is 3.5. A steel knife or a glass plate, we use glass plates, which is 5.5, a steel nail, 6.5, and a masonry drill bit, which we don't have, so we won't be using. Frederick Mohs, the guy that created this, gave a scale of 10, base 10 of things that are known. So talc is going to be our softest mineral at a number 1, and diamond will be the hardest at a number 10. Quartz falls in there at a 7. Calcite, which is what marble's made out of, or kind of has a hardness of 3. The scratch test helps us in the field because it doesn't take a lot of bulky tools, and even though some things have the same color, like quartz and calcite, a simple scratch test will tell us which one it is. The next thing we're going to talk about is the luster of a mineral, which is the way that a mineral reflects light. The main 2 lusters that we're going to talk about in this class are metallic and non-metallic luster. Metallic luster doesn't necessarily mean that it's shiny, but more shiny like a metal. So while this one on the right over here that says vitreous is shiny, it will reflect light, we don't say that it has metallic luster because it's not shiny like a metal. These are just a couple examples of lusters that we can see. Galena on the left has a metallic luster. Amber in the middle is resinous. And then the quartz on the right has a glassy luster. Here's a couple other lusters that we can have. In class, we'll definitely see some of these pearly ones on the lower left. The greasy ones, the second lower left. We have a bunch of earthy lusters, which will just look earthy, kind of like dirt. The next property we can use to identify minerals is density. We should be very familiar with this one by now. The density of minerals varies widely from about 1.01 grams per centimeter cubes, just denser than water, to about 17.5 grams per centimeter cube. In the field, geologists don't really use density to determine what mineral it is because the equipment that they would need to take is bulky and kind of a pain in the butt to deal with. But it is another way that we can use to discover minerals. In the field, scientists instead do a relative density test and they see which item about the same size is heftier and thus more dense. The next thing we're going to talk about is cleavage and fracture. Cleavage and fracture is the way that minerals break. So if a mineral has cleavage, these are all pictures of cleavage right here, it's going to break smooth along planes. Muscovite mica, which we'll see in class, has one plane of cleavage, so it's breaking in these flat sheets. You can have more than one plane of cleavage. Two directions, the example is feldspar, so it will look kind of like a stair step. Cleavage in three directions, our example is halite. It will look like blocks built up on each other. And our last example of cleavage is this calcite on here. It has cleavage in four directions, so it kind of looks like a trapezoid-ish parallelogram. All of these things here are going to show cleavage. This one in the top left is our muscovite mica. It breaks off in flat sheets. Next to that, on the upper right, we have calcite, which looks like a cube. It's going to have the three planes of cleavage. Down at the bottom, fluorite, you can see has cleavage. Even though it's prism-like, it's still going to break flat along those planes. Opposite of cleavage is going to be fracture. Fracture is going to be when something breaks rough or jagged. There's normal fracture like these ones where it just has no breaking pattern, and then we also have what we call conchoidal fracture, C-O-N-C-H-O-I-D-A-L fracture. This one breaks off in these ribs, or kind of like the inside of a seashell is what it reminds me of. Quartz does this. Obsidian, that comes from magma cooling really quickly, does this. So we either, with our minerals, have fracture, meaning it does not break in planes, or cleavage, which means our planes are going to be smooth and pattern-like. The physical properties which we just talked about were used by scientists from the Middle Ages to the 1800s as the primary means of identifying minerals. In the 1850s, 1860s, this mineralogist right here, James Dwight Donna, developed the classification system, which we talked about last class, dividing minerals into those 6 groups: silicates, oxides, carbonates, native elements, sulfates and sulfides, and halides. So prior to Donna, minerals were arranged by their physical properties like hardness, so diamonds and corundum would have been in the same mineral group. After Donna implemented this system, minerals were classified more according to what was in them and how they formed. So minerals that were found near each other were likely to be in the same mineral group. We know that silicates is our primary mineral group on Earth, and that 90% of Earth's crust is covered in silicates because magma has silicon in it. However, uncommon minerals that we find on Earth are also crucial. Galena, which is in the sulfides group, is where we get iron ore. There's also apatite, which has phosphate groups that we extract from it to use as fertilizer and other things. That concludes our video lecture for today. You need to complete the quiz on Google Classroom before class starts on Wednesday. Have a great day.